So for this differential pair, oh yeah, this is a netlist with a startup circuitry. We'll talk about we already talked about the voltage gain, common mode voltage gain. We can talk about the frequency response and also noise, equivalent input noise voltage. See, let us see. This differential pair is simple, very simple. Differential pair, NMOS input. See, I have a NMOS input transistor, and then I have a cascade current source. So this is connected to that constant GM bias circuit. And then this PMOS has just a current mirror. So this one is called active load. This means usually load is, we use resistor, right? R load. But in this design, we use a transistor as a load. That's why it is called active. Okay. Oh no. Yeah. For the low frequency, let's see. Yeah. Usually we use this one as a differential amplifier, right? Say I have a common mode input and differential voltage here, and the common mode input minus differential voltage here, right? Yeah. So, yeah, for this differential pair, for the differential mode circuit, I mean, say when common mode, when VIC equals 0, then this becomes a virtual ground, right? AC 0. AC 0. And then this looks like a common source amplifier. So differential amplifier is a collection of two common source amplifier for the differential mode input. Okay. Yeah. Let's talk about the low frequency voltage gain. Yeah. Say we have a differential mode voltage gain, which is GM1 times RO. Okay. GM1 is transconductance of this M1 transistor, because this is connected to constant GM bias circuit. All the transistors here, that GM, those GMs are proportional to that 1 of R. Okay. That's the advantage of a constant GM bias circuit. Okay, we can control GM by changing R. Yeah, for the common mode voltage gain, low frequency voltage gain is, let's see. Oh, this is the resistance, small signal resistance looking downward. That's RO1. Okay, then the common mode gain is just 2 RO1. And then I think this is divided GM3 RO1 RO3 times RO. Okay. So if you compare those two, yeah, this low frequency differential mode gain will be much larger than common mode voltage gain, right? Low frequency common mode voltage gain. Yeah, before going to the frequency response, any question?
Actually, here we take the output from this LZ2 and LZ1. If I take the output is PC2 and PC1, and this circuit will change.
Can you repeat the question?
Here I take constant GM bias. We take the GM2 and the NG1 and NG2.
Okay, let's clarify this. I assume symmetry, okay? So I assume symmetry. They are symmetrical. Okay, then what's your question?
My question is NG1.
NG1. Oh yeah, this thing, yeah.
But if I take it is a PG1.
PG1?
Yeah.
What do you mean by PG1?
In the last circuit, we take for the value PG1, PG2, and NG1, NG2.
Oh, you are talking about PG1, yeah. PG2?
Yeah.
That's for PMOS.
Yeah.
Right? So let's see. Where is the current circuit? So this thing is actually PG1, right? Yeah. This is NG1, right?
Yeah.
So this should be connected to PMOS, okay? Yeah, because see, it must be connected to VDD. The source must be connected to VDD, something like that, okay? Those PGs for PMOS, which is sourcing current source. This is connected to NMOS for the sinking current source, okay? Something like that, okay? Yeah, we cannot use PG1 here. Okay, let's look at the frequency response. See, for the AVDS, frequency response. Yeah. Yeah, for this case, we are considering differential mode signal only. M1, M2, M3, M4. Yeah, this is a VDD. And then let's just see. Yeah, see, the small signal resistance looking toward the transistor that output is RO, then I have a CL, so I have a pole here. Then see, for this case, see, I am assuming implying T equivalent circuit here, and then see the small signal current flowing through here is half GM1 VID, okay? Yeah, this say I can say this is ROCL parallel. The current flows through into parallel connection of RO and the CL. Okay, and then I have another current path. You know, this current flows through here and make a copy of that one. So this also flowing into there, right? So this current is another half GM1 VID, right? So my VO is just two currents, half GM1 BID times 2 times parallel connection of RO and CL, right? Yeah, this one can be written as RO plus 1 plus SRO CL, right? That's a parallel connection. There is one more point here. See, there can be some capacitance here, which is C3. We've seen two signal flow paths. One is a signal flow through here. This is the first signal flow. Second is a signal flow path through there. And then see, this is AC ground, so there is no capacitance involved here because that voltage never changes with the time. However, this voltage changes with the time. So, there is asymmetry. All right? So, the small signal resistance looking here is 1 over GM3. That's resistance there. So I have a pole for the upper path. This is signal path 1, signal path 2. For the signal path 2, I have a pole generated by 1 over GM3 and this C3. Okay? Then, yeah, my VO changes. So my VO, the lower path, half GM1 VID times that RO parallel CL, okay? And then plus 2, number 2 path, which is, there is one more pole here, actually the same thing there, and then there is one more thing involved here, which is 1 over GM3, 1 plus S 1 over GM3 times C3. Okay, this is a pole, effect of a pole. I need to add them together. Oh, then there is a C. Let's see. This is something wrong here, right? What is that? Oh, sorry, this should be 1. Numerator must be 1. Okay? Then, let's see, yeah. If I add them together, what happens? Let me see. Yeah, it should be GM1 RO 1 plus S RO CL VID times, let's see, I think we'll get something like this equation. HEP, is it HEP? Yeah. 2. There is 2 here, right? 2 here, 2. This is a 2 divided by 2, something like that. Is it right? Yeah, something like that. So here I have a dominant pole. This is my dominant pole, 1 over ROCL. And then I have some non-dominant pole. I have, this is some mirror. This is some mirror generated by mirror 0, right? Mirror 0, mirror pole, mirror 0. So my frequency response AVD will look like, say, this is dominant 0. This is a border plot. 1 over ROCL here. And then I have some, which comes first? Is it? This comes first or that comes first? Let us see. This is 1, right? 2 plus something. Yeah, this 0 comes later. S divided by think it's something like that or something like that. Yeah, this pole comes first, and there is some zero there. So I thought the other way around. Let me see. I added this thing here. Just 1 over S C3 GM3. Oh, sorry. 1 plus 1. What's this? 1 plus SC3 GM3. Just 2 plus SC3 GM3, right? So this 2 goes away. So this is correct. This is correct. Then, SRC. Yeah, this comes first. This comes later. Okay, question. Nope. 정경원, any question? No? Okay, how about the common mode gain? For the common mode frequency response of a common mode gain is something like that. This is M1, M2, and then M3, M4, something like that. Okay. For the common mode input, see, this has a pretty large resistance. This RO something, RO1 or RO2, pretty large, and this voltage is around the VIC because RO1 is much larger than 1 over GM. Then, in a differential mode case, this is a 0. However, this can be replaced by those parallel connection C1 and the RO1, right? C1 and the RO1 parallel connection. So common mode current, see. Common mode current flowing through here will experience this pole. Actually, this is actually 0. Okay, yeah. My common mode current can be written as VIC 1 over GM1 in series with that RO1. Oops, no, this is 1/2 GM1 because I'm taking those 2 transistors in parallel, and then this RO1 S RO1 C1. Okay. Then see if I rearrange this thing, and then I find this RO1 C1 in the numerator, and then in the denominator I have some S equation here. Okay. So I have a 0 at the 1 over RO1 C1. Okay. So yeah, because this VO is just I1 times actually this I1, and then this is reduced by this M3 because this I1 copied there and it cancels that. However, because of that asymmetry, so this will be reduced by GM3, RO3, RO1. Okay. Yeah, that's my current, and then this is RO. Yeah, that's my VO. Okay. So anyway, because I1 shows up here, my 0. I have my 0 for AVCS. So in a common mode, Bode plot looks like that. So at the low frequency, it's very small. However, because of this 0, so it goes up, something like that. So I want small common mode gain. However, it increases at a very low frequency, right? Question? No? Oh, finally, Mr. Lee wakes up. Any question? Huh? 이원철. Question.